also to have some feedback from you about. So the rationale of the project is, of course, the problem of floods. So floods are one of the most common and costly natural hazards in the world, and the catastrophic floods endanger life and cause human tragedy, as well as heavy economic losses. The plot that you see on the right are mainly the data sets, the data that EMDAT collect for Europe in the last 40 years. And we count like 600 events of floods that produce more than 4,000 deaths and more than 12 million of affected people and more than 140 billion of US dollars in damages. So it means that flood forecasting system is extremely useful and essential to mitigate the societal impacts of flood events. To do that, we need, of course, input data, and we need information from key variables. I listed here just a few of them, like precipitation, soil moisture, water level and river discharge, and flood extent. And we know that satellites can offer a solution to provide this kind of data, but also a large coverage, both in spatial and temporal. So here just a list that we can see later in detail, but just to highlight that satellites techniques now are quite in advancement, so we will have more data in the future, and it is time to invest in this kind of technology. So how to integrate satellite data into the flood forecasting system? There are 4 different ways. So if we think about pre-event, we can use the satellite data to set the initial conditions of the model, to calibrate the parameters of the model. During the event, we can use satellite data in the assimilation mode. And post-event, we can use as well the satellite data to validate the output of the model. And so EO4Flood, this project aims to develop a new generation of flood forecasting systems that integrate both the cutting-edge EO data and advanced hydrological modeling. We use also AI tools to support this integration. And the goals of this initiative are structured around 3 main pillars. The first one is the creation of an Earth observation dataset. So we will have this global dataset that we use for the scientific community, so it will be free and open access. Then this dataset will be used into the flood forecasting model. And finally, we will demonstrate the utility of the data and the modeling for the science and the society with 3 case studies. I will go into detail of these 3 pillars. So about the first one, I have to say that we will develop the Earth observation dataset for these 9 basins across the world, mainly focused on Europe and in the global south. So the dataset will be delivered in all these 9 basins, but the flood forecasting exercise will be processed just over the light blue basins. So the Niger, the Negro River, the Congo, the Brahmaputra, and the Torn in Sweden. About the global datasets, we will use the precipitation, soil moisture, and snow already processed. So we just collect this data from the different platform and data available online. But for the rest, we will generate these other variables that are quite useful for rivers. So river width, the surface reflectance, the water level, and the slope. And we use all these variables to derive the river discharge in order to have this multi-sensor, multi-mission river discharge product, because we have seen that if we merge more information, we could have more chance to have enough a reliable product of river discharge also in time. And then, of course, we need the flood extent for the map of the inundation. So all these data sets will be provided just from satellites. So I will go quite fast, but here is a list of precipitation products that we extracted and collected from the platform. So you can see just pure satellites products, reanalysis products, and also gauged products. For soil moisture as well, we have several products also in the near real time, like the H121 from EUMETSAT. For snow, we have different products, and they will be provided just for the Torn River, at least in the mandatory phase. And we will see if we can provide also in the rest of the European basins. So, and we have snow cover area and fraction, snow water equivalent, and snow state. And then we will have these variables that are more, let's say, in development. So on this respect, we use the approach of Stuttgart that derive river discharge from the width of the satellite. So they will use product of optical sensors. And like the classical approach of rating curve, they derive river discharge. In a similar way, we use the surface reflectance. So in our lab, we developed this methodology to use the different classification of the area around the river, and we combine this different area to derive an indices, some indices that are defined like a proxy of river discharge. For the water level, we use the datasets already available on Daiti. They have plenty of virtual stations, more than 10,000, derived from different altimeters, from the TOPEX Poseidon to the recent SWOT mission. And into the project, they will provide also the near real-time data that are not still available on the website. All these datasets are also have also uncertainty into the value. And we use the water level in a different way, in the sense that we use more than one mission to derive the water level from altimetry, because we know that altimetry has a raw temporal resolution. And so as an example, here you can see the longitudinal profile of a river reach, and the different color in the upper upper plot referring to the different mission. Below, you can see the SWOT measurements into the same river. So immediately we can see the added value of this recent mission. But if we use both, so if we use more than one mission of altimetry, we can get this plot in the upper part in the top right. That is a plot of temporal and spatial value of this river reach in time. And from this, we can reconstruct the time series. So a dense time series take into account all this information that we get from the satellites. This is very useful to derive a dense water level, because as the traditional rating curve approach, we can estimate river discharge from them. Indeed, as I mentioned already, the river discharge will be derived from single variables to get finally into a multi-sensor product. Because we have seen that in previous studies and previous projects, we have seen that if we use just independent and single mission, we could have or good performance but low frequency, or lower performance but good frequency. But if we use both, we have more possibility to have frequent information. That is what we have, what we need for flood forecasting. Finally, we have this flood extent product that we derived from three different missions: Sentinel-1, Sentinel-2, and VIRS. And in summary, we have so far 12 flood events that have been extracted over 5 river basins with a lot of images and flooded inundations. And yes, so all these data sets of satellite data will be ingested into the flood forecasting model. So as I mentioned before, the way to ingest this data are listed here. So data simulation, initial condition, data forcing, and calibration. And for each model, we plan to use several models already implemented over these basins. And specifically, we focus on these two, the Niger and the Negro rivers, in which we are able to compare all these models for just also to see the potential and the limitation of each models, and also the AI approaches. So in these days, DHI is developing this new tool. When the model are many, we use also the probabilistic forecast for having this the probabilistic forecast, and then we use the data for the hydraulic model. So each basins, from each basins, we selected a river ridge in which it is really interesting to provide the flood forecasting and the flood inundation and discharge and water level and so on. And we use different models already implemented there. So the final purpose is to have the water level and flood extent over these areas. Finally, the third pillar is the impact assessment. So we study 3 case studies. The first one is the impact of dam in the river regime, because of course EU offers this possibility to monitor the dams, and the land use change impact in flood, so we can assess the impact of land use change in flood occurrence, and finally the variability of the population trends, flood dynamics, and the impact on the flood exposure. So, so far we have seen we built this project always based on the experience and the relationship that the partners have with the stakeholders. So in terms of insight on capacity building and community engagement and communication, we can say that the selection of case studies is based on the ongoing activities in which the project partners are involved. And these initiatives rely on consolidated networks of collaboration with institutional stakeholders, and I mentioned just a few. The capacity building, so it is not in one way, but it is active because we actively co-design the study areas, the projects as well, and the stakeholders are directly involved in identifying a critical location where flood forecasting is needed, and also to adapt the flood forecasting system to the local operational context. Of course, the early engagement with end users is good because we have these preliminary discussions, and we can facilitate the integration of also of the Earth observation datasets into existing forecasting systems. And then in the future, we are planning to have dedicated meetings in which stakeholders and local experts will be invited. And in this case, we can have discussions, and we can also understand the relevance, the usability, and if the local needs are satisfied. And this process improves, of course, the local technical capacity, promote ownership of the tools, and supports the long-term usability and sustainability. And in terms of again, the engagement and the communication, we have this interaction with stakeholders almost quite often. And so we have these regular meetings with the end users, especially the different partners have this kind of relationship. And then the project has already a lot of outreaches. So we participated to several events with major scientific events, and we have also web stories published by ESA. We participated in the Agora sessions to have talk and stimulate the exchange. And yes, the open science in the sense that with these community data sets, we have more chance to foster transparency and reusability of the data sets. So it is very useful to have this open access science. The lesson learned so far is that, of course, the limit of satellite data is the latency of the data. This is an example, 3-5 days is the latency of the water level from altimetry. And of course, it's quite challenge for the small basins. The global coverage doesn't mean universal applicability. So it means that hydrological complexity hinders consistency across regions. So, and it is not easy to adapt for everywhere. The daily resolution is hard to reach, again, because we don't have the design of the missions adapt to this kind of resolution. The in situ data is often missing, but if we involved stakeholders, it can speed up this kind of sharing data, and also is good for the project, for example. Interdisciplinarity is like an innovation, so collaboration bring always new stuff, new algorithm, and new collaborations, and data sharing boosts collaboration and trust. So as I said, open exchange of data across institutions of course, science needs translation. So it is extremely strategic to have flood maps and return periods easy to understand for decision makers. So I leave here with this with the website of the project. You can scan the QR code and have access to the website, and in which you can find the different the deliverables that we have done so far, and some outreach and some educational material. So thank you for your attention, and I'm here to answer to your question.